Hello reviewers, welcome to my channel Science to Technology. In today's show, Future Friday, we're going to talk about battle for motors of tomorrow. So let's dive deep into it. Now here's the deal. I am pretty sure I do not have to explain to you, but we all run on motor. Be the smallest thing to big puppies, all of them run on motors. Be it your washing machine, be it your air conditioner, or be it your heater, or be it your locomotives. All of it runs on it, from smallest thing, toys level to aircraft level. Everything runs on motors. And here's the ironic thing. Once humanity starts to grow, like a civilization, take a country or whatever have you, they start to grow, they start to seek efficiency, because again, there will always be a limitation how many power lines you can draw, how much current you can draw. Like again, assume you have magical power source, you still have the issue of delivery. How the heck are you gonna deliver bonkers amount of power? So doing more work with less actually becomes a bottleneck remover. So as civilization grows, they naturally remove the environment, remove the carbon dioxide, naturally wants to move towards, hey, we can do more with the same thing. Because again, in the old days, you only had one or two appliances, who cares how much current it was drawing. But now you start to have so much appliance that it's like, whoa. The current that is, like the line that is coming to my house, let's just say it's rated for 100 amps. Now you have a limitation. So fundamentally, the more you grow, the more efficiency people will chase. And that has two primary advantages, multiple, but those are two primary. First, less waste heat generation, meaning if you have a motor, take that motor, whatever have you, whoever manufacture whatever topology, take it and run that motor at 60 degrees Celsius. Make sure it will never exceed 60 degrees. It will last practically forever. Take the same motor, same batch, same everything, and run that puppy to 100 degrees Celsius. It will work. It will even survive few years, but it will not last forever. So fundamentally, if you have less waste heat, the running temperature of the motor always becomes cooler. That means it will last longer. Another aspect, lower running cost, which means money saved. So how many types of motor exist? Practically speaking, way too many. Like odd infinitum amounts of motor exist, and how they are geometrically laid and how they are driven. Basically, the moment we started to do electronic commutation, basically on and off the stator coil, yeah, odd infinitum combinations exist. So that is there. But here's the, there is no one motor like this motor is the thing. That does not exist. Key thing is fit. Does it fit your need? For example, you are making basically a room heater. You're not gonna put, okay, this is a room heater, let's put the most efficient motor in it, let's say 3-phase AC motor that is like, very tight air gap and copper rotor, so it's very efficient. Yeah, people are like, no, this is a cheap use and throw item. It cannot have motor that expensive. So they will use shaded pole motor. Super cheap, effective, not efficient, but effective for that fit, where it's like use and throw motor. That is cheap enough to do that. Let's say your washing machine, it does not need bonkers amount of what you call efficiency, but it does need motor with flexibility, meaning the motor should be able to work at low RPM, high RPM, clockwise, anti-clockwise. So universal motors are chosen for it, and now BLDC is making sense. Again, the only reason we can do that is not because BLDC did not existed back then. They did. It's just that electronic commutation of it became cheap enough, cost effective enough that it can be done on something that is low cost as washing machine. So let that be very clear. It's never about this is the best. It's always it fits the requirement. If you ever wondered like what the hell engineers do, this is their job. Sit down and figure out what exactly fits under the given constraint. Everybody wants the best. It's just nobody wants to pay for the best. So start with the simplest thing, geometry. Now geometry is basically how the heck magnetic flux flows. Flux are lines. So how the heck it flows. So radial, basically normal motor. Imagine a motor in your mind. You are imagining a radial motor. So that has rotation like this, and magnetic flux. Radial flux is a radial, meaning 90 degree. It's going like this. Basically magnetic flux. That's how it's going. So this is what we call a radial flux. Axial flux, if it is rotating like this, the magnetic lines are also parallel to it. Parallel. Magnetic flux and rotation shaft, they are parallel. If they are 90 degree, they are what we call radial. Now here's the deal. Radial is a sorted technology, meaning every single aspect of it is done. is sorted. We good. We got this. How do we manufacture it? We got this. How do we mass produce it? We got it. Meaning the rotor and stator, if a company has to start a motor with this sort of axial flux topology, they can optimize it so much that it's like they're going to take one sheet steel, one roll of it, and punch the stator, and in the center part punch the rotor also. So very effective, very easy to mass produce, everything. How the heck you gonna wind coil? 10,000 companies that make robotics for it. And I mean manual robotics, just like spin wire into this, punch it through it. We good, we got this. Everything about it is sorted. And they have torque. This geometry gives you torque on a level that you cannot imagine it. Like this has so much torque, locomotives is like it push through the locomotives. Like, come on, man. So much torque that it moves submarines through water like brah, come on. It got torque. So these are torque monster. Now we come to axial flux. Now axial flux are older. Which again, I'm reasonably sure all of you have studied this in your scientific books in class 4 or 5. This sort of motor where you spin it and like, it generates power. The world's first generator and all that. And yes, generator and motor are the same thing. So fundamentally, again, you can't spin this without commutation. You would need either AC frequency or BLDC circuit to drive it, but it can be driven. And yes, motors were also created, not only generator, motors were also created that were axial flux very early on. And I mean like before Nikola Tesla became a normal thing. So why don't we use it? Well, it's too hard. Meaning everything about this is goddamn difficult. For example, stator requires something that is magnetically very concentrating. Basically, it allows the magnetic field to be concentrated, but made in such a material where it's like, insulating. So electrically it's not shorting, so it's not creating eddy current loops. So you need something that allows magnetic flux to pass, and you need something that is insulating enough. Silicon, steel, your choice. Oh, perfect. How the heck are you going to stamp it? This stamp, stack it as much as you want, the end, go home. How the heck you stamp on an axial flux? You can't. You literally can't. I'm not joking. Like China had to come up with a tape machine device where it's like it's a tape. They are spinning the tape and they have a machine that is calculating how far each stamp has to be. So it creates a slot like this, slot getting bigger. And again, you must understand it requires calculation in order to space the thing, not just like patam go. So, other companies are like, okay, we're gonna just have spring roll of that silicon steel, and then just we're gonna have an end mill carving a path, which again causes eddy current performance loss. A lot of issue is there. And even if you solve all the stator and rotor manufacturing issue, the one structural issue that destroys it is the bearing. This puppy is bad for bearing, meaning if I give you the same bearing, right? Let's say conical bearings, and you're like, one is this, same bearing. And if I give you, let's say, 1 foot of gap, this puppy will last forever. Same bearing, I shrink it, it will not last forever. So fundamentally, axial flux are far brutal for bearings. Like they're bad for bearings. Radial does causes a penalty. Now your structure has to be rigid enough. It does have that penalty, like, oh, it has to be robust, strong, so it does not twist, so the shaft remains in the alignment. Yeah, that's the penalty. Benefit, that puppy will last forever. Like those bearings is like, bro, we got this, we good. Put it, forget it. So these are the geometry part of it. And again, let that be very clear. How do you select between them? It depends on your need. For example, this is a cement truck. They needed a motor that is powerful enough and that can spin that drum, the cement drum. This is like, bro, I can do this. Now, could a radial motor be powerful enough? Of course. Would it physically fit? No. So that's the whole point. For example, electric aircraft, they need something that is very compact. This radial will not fit that bill. Axial will. That's the whole point. Right fit for the right job. Now, could you use axial flux motor for electric vehicle? Yes, you can, but it's like unwise, not necessary, overkill. And that's why if you look into people who do actual teardown, most of the time motors that are actually sold, millions of them, most of them have this. Why? Bearings. You do not want to sell a motor where it's like, hey, I sold the motor. Yeah, my electric vehicle kaput itself because the bearing went kaput. Bearings do not like axial flux. They hate axial flux. So this is the geometry part of it. Now we come to coils. Now coils are the thing that actually makes motor or even generator work, because they convert power that goes into it into magnetic flux. So it comes, power goes in, electricity, and magnetic flux comes out. Now limit of the power is there, because again, we are not talking about magic material. So there are multiple vectors of it, three main vectors. First vector is insulation, basically how much voltage you can do. For example, industrial motors, because they need so much power, like, megawatt class power, they can't afford to have, like, mains voltage, like, 220 volt or something like that, or even 600 three phase. They can't afford that, like the current would be too huge and copper is too expensive. So they're like, hey, increase the insulation, basically insulation becomes thicker and high voltage rated, so they can run it directly on 11 kilovolt, but the current goes down. And copper is more expensive, so it makes justification. So insulation defines how much voltage those puppies can handle. Another aspect is how much current the wires can handle. Current is directly affects the copper. You can replace it with silver, but good luck if you have that kind of money. So copper has a conducting capacity and you have to design according to it. Then we come to the third element, basically how you are dumping power in and out from it. Frequency. So frequency wise, whenever we are talking about frequency, it has a skin effect, meaning at low frequency, as in like what we use 50 or 60 hertz in AC mains, does not matter that much. The moment you start to go high frequency, like if you go into aircraft, if you have ever taken a video and if your mobile phone did not know you are in aircraft, it will show you a lot of thin lines. Those lines are 400 line. Normal frequency is 50 or 60 hertz. Aircraft, because they wanted to make small motors, small compressor, everything required so much power, they needed a way to make those small things. How can you make it small? You can't increase the voltage, you can't increase the current carrying capacity. What else is left? Frequency. So go from 50-60 hertz design to 400 hertz. So that allows you to get more work done because RPM goes up. But it does not like copper at that point in time, meaning skin effect is created, meaning if you have like, okay, what if I have thick copper bars? Yeah, it will not able to carry the current. It actually will have less current carrying capacity. Why? It creates eddy current fields inside the conductor that pushes the electron outwards. So only a thin skin is utilized, and higher the frequency, the worse it gets. So for example, if you are making a spindle motor that could go very stupid RPM, yeah, you have to use round wires and you have to make them very thin in order to utilize it properly. So fundamentally, skin effect is a big issue. PCB coils, they are becoming a hype thing now. They have air core. Now this should be the one thing that you must understand. This is how you figure out issues between marketing hype and actual factual hype. PCBs have what we call air core. Cool, awesome. They have lower iron core loss. Factually true, but that should trigger a red alert in your brain. It's like, if iron, basically that silicon steel has this much losses, why the heck anybody puts it? Yeah, that allows you to have torque density. If you remove that, can you remove it? Of course you can, but your torque density disappears if you do so. So if you are like, hey, I want a 10 megawatt motor, yeah, try to design that with PCB. Yeah, it's not. You're gonna need way too much to do it, like size wise, size wise. But if you're like, I want it compact, yeah, it has to have something that allows the magnetic flux to be channeled. So that's why if you want a torque monster, you have to deal with that basically penalty of iron losses. And that's why like all motors still have stator and rotors that are like, stamped steel for this exact reason. And hairpin, that does allow you to improve basically how much copper you have in each slot. That's the thing that they say, hey, you have more copper in your slot, so you can send more current. Yes and no. You can send more current, but not if it's high frequency. And again, electric vehicle motors, they are this small and they're like 100 horsepower. It's like, how the heck you have that much horsepower? Oh, the voltage is not that high. Current is also not that high. It's the frequency that is stupid. So it starts at 400, goes to much higher than that. Like, I don't even know the upper limit, and I'm reasonably sure there is no upper limit, but give or take, I would venture, my guess is like 2 kilohertz maximum. So that's why having that sort of copper system, it will only give you one benefit, that it will be able to conduct heat far effectively. Again, if you need that, cool, but if you don't, there's not that much benefit. Again, skin effect is fighting you. So you can put that in a rotor. If a rotor has electromagnets inside them, those will be running on DC. That will make perfect sense for that. Or if you are making a motor that has a very low frequency system, you can use that. But again, if you need high frequency, you have to use round wire. That's why round wire did not disappear, even though every Tom, Dick and Harry was hyping up a hairpin winding for like, I'm pretty sure 10 years. But that's the whole point. You can use it. You can laser weld it and do this and all that. Cool, awesome. It's just that, what's your frequency, my man? If your frequency high, yeah, you can't use hairpin. So that's the balancing aspect. Round wire is very messy. That's why people don't like it. You have to like wind it. It's not just like, okay, put the slot, laser weld, go home. No, it's messy. But it's basically, while it is hard to make, it's very good balance in all vector, meaning you want current carrying capacity, you can use thick round wire. You want like, lot of oomph, it got you. You want heat, high tolerance, it got you. It's all rounder. It's a very good all rounder. And you're like, okay, what if I want to use superconductor? Wouldn't it make it more efficient? Very big red alert. Big motors are very efficient. As in, the world record is 99.13% efficiency. Guinness Book of the World Record, ABB made it. It's in India. And that's 99.13% efficient. A superconductor will not make you efficient. It's like, then what's the point? It will allow you to shrink it. For example, this is a Navy puppy. So I'm pretty sure it's a destroyer or something like that. Basically, US naval destroyer was like, hey, we are running out of space. So they have a ship, cool, awesome, GG. And they're like, okay, we have a power plant somewhere else, jet engine power plants, and we want to drive the propellers. Cool, awesome. This is the motor that they were got spec'd. So this is a copper motor, 36 megawatts, so big puppy, 120 RPM, high torque motor, 6.6 kilovolts, cool. 180 tons. This puppy is heavy, or that was the last spec they got, and it can go up to 250 tons. So like, eesh. Now again, this is normal. There are a lot of destroyers and ships that have this. Like, this is like take it and go. But they are like, hey, what if we want next generation performance? They're like, okay, what if you make superconducting? Now, superconducting allows you to have the same 36 megawatt, 120 RPM, 6.6 kilovolt at under 75 tons. So you are literally 1/3 the weight, and size-wise, you almost shrunk it by 1/5. Now, is there a benefit of it? Yes. This allows them to carry more fuel, liquid fuel to drive those jet engines, or more missile pods, because again, the space saving matters. So that's why people go to superconductor. Do not fall for that, oh, superconductor is more efficient. It would be more efficient if you are comparing it to like hyper cheap single phase AC induction motor that is like made for use and throw items. But any high efficiency motor that is designed to be efficient, it would be efficient. Like a superconductor at best can give you 5% efficiency. It's not a big deal. Then why? Again, size. Size means a big deal. The moment the destroyer designer say like, wait a minute, I can put longer missile cells. Shut up, take money. So, oh, and that's the water use. Air use is coming online right now because all the 6th gen fighter, they want to realize a big issue with fighter jets is that the engines do not start. Engines do not start. If you have been in any airport, you know that jet engines do not start. So what do? You have a small jet engine that you electrically start. It runs a big ass compressor. That big ass compressor feeds air to the main turbine, and then it starts to spin up, then spool up, then ignite the system. What if you want to make a very efficient plane? How the heck are you going to start the engine? Like if you are dealing with SR-71, they had almost like a Mustang kind of engine going YOLO on a compressor. That's how they started. It's like messy. How would you do that on 6th gen? Well, put a superconducting motor there. Now it's a small one. It's like this size, 2 megawatt. I've seen some designs that are trying to do 10 megawatt. But 2 megawatt, and the benefit of that is it's a motor generator unit. It can direct spin start it and leach all the electrical energy directly from it. So they can really, give that much power. Like, why do you need megawatts of power for jet engine? Fighter jet. There are only 2 things that consume that kind of power: radar and bonkers amount of laser power. So that's the 6th gen. They are also using superconducting systems. So let that be very clear. Superconducting does not mean high efficiency. Necessarily, it necessarily means smaller size, small puppy. Now we understand the principle of these motors that we are talking about. There are only 4 ways of spinning it. You could talk this and that, but there are only 4. So these 4 principles are induction, reluctance, magnetic, electrostatic. We're not going to talk about electrostatic because I do not listen to anything that starts with, oh yeah, it starts with 1000 kilovolt or again, it's supposed to be next to human. I'm like, industrial motors go much higher, but again, they are industrial, a big, huge behemoth thing. Electrostatic has to be at that voltage. You cannot shrink it down. I'm like, no thanks, me cool. So these are the 4 main systems. 3 of them are the primary daddy. So induction, Nikola Tesla gave us, like, this is the GG. What does it mean? This simply means it self-starts. This is one of the few motors that can actually self-start. You give it AC mains frequency, it will start, it will reach its slip velocity, it will be fine. It's like, I got this. And it has GG lock torque, meaning when you're starting something, you need insane amount of torque. Induction is great at that. It almost auto compensates, meaning if it needs more torque, it will give you more torque. It's like, and that's why if you look into basically compressors, they always have a saying, locked rotor current. It could draw almost 3 or 4 times the current rating because it will try to overforce it. So induction motor is great in that. Like, it's super cheap, super reliable, self-starting, and great torque. Then we come to reluctance motor. It's super cheap because again, the squirrel cage is thrown out. You just have stamped steel, and it is synchronous, so it is bit more efficient. Not too much. Let that at the right sweet spot, you can find reluctance motor that is similar price to induction and more efficient. But induction can be made very efficient. But it's just that it becomes so expensive that reluctance motor makes sense. Then why don't we use reluctance? Yeah, it does not self-starting. You need electric commutation, or in the ancient time, before induction motor were made, reluctance motor had like a post that has small split rings that was spinning, and you had to start it. Once you that brush starting, it will start to do, but it was horrendous. And again, if you're like, how the heck we had DC motors? Yeah, most of them had commutation via brushes. Remove that. Induction not need it. That was the genius of Nikola Tesla. So reluctance is super cheap hardware, but again, your money goes into your electronics, and it is synchronous, so it can be more efficient depending, like again, at certain points, certain operational range of torque and voltage and everything, induction may become inefficient compared to reluctance. Then we come to magnetic. All the old DC like that actually used to drive trains and all that had brushes, those were electromagnet. So electromagnet or permanent magnet, these are the two principles you have inside magnetism. Now permanent magnet had the same problem. It could not self-start. So it requires electronic commutation, meaning your BLDC controller is going there. Where is the rotor? Okay, rotor, yeah. Okay, rotor, move. If it did not move, it will keep trying to do that. It will keep trying to do that. And it basically moves it. That's why you cannot just plug in like, a 3-phase AC and expect it to run. Only induction motor is like, I got you, fam. Or universal motor. But again, universal motor has too much brush noise. But induction motor is like, that's the greatest advantage of induction motor. It starts, it does not need microcontroller, it does not need brush, it does not need magnet. It's like, bro, I got this. And it fights for you. So starting current is awesome. So that's the whole point. Electronically commutation is necessary. Now, the best motor is AC synchronous motor topology. Here you have two options, brush motor or brushless motor. Now brush, because you are sending a DC current directly into the rotor. Now why would you want to do that? Well, to control the output. For example, if the torque is over, like you are creating too much, you are creating a reluctance in the magnetic field that is causing you a poor power factor. You're like, hey, what if you don't want naughty power factor? What if you want power factor of 1? That means you have to balance the loading. How do you do that? Control the electromagnet that is in the center. That's why they brush. Now, like, why this brush is not bad compared to universal, that is bad. Brush comes in two variety. One is split, another is slip. Slip slips. It does not fight with you. It slips. It's smooth. It's long lasting. All you are already using it. For example, your car has alternator. Alternator has that. So slip ring, don't worry about it, it will last forever. All your coal power plants, they have that. Nuclear power plants have that. So yes, those generators can be used as motor. And yes, European Union had brain where they're like, hey, we are adding so much renewable, we don't have inertia. They took the old decommissioned basically generator, turbo generator in the coal power plant. All the wiring were already there. They're like, okay, throw away the turbine, put a big ass flywheel, spin it. Now you have grid inertia. So AC synchronous motor is the best. It actually stabilizes the grid and can run at power factor of 1 without active electronics. So that's how you do that. Slip ring is there, and you can remove the ring. For example, this is the same AC brushless synchronous motor. Now, like, okay, if brushes are not that bad, why would you want to remove it? Well, if you are working in dusty environment, or you are working in a boom environment where something can go kaboom, at that point in time, you're like, especially dust. Because be mindful, all the turbo generators, yeah, they have hydrogen as cooling. So yeah, again, they still have slip ring. But again, if you have dust will gum it up, grind it, it's unsafe. So at that point in time, they use exciter. I'm not joking, that's the name, exciter. So you have a stator that gives you the main power that goes into the exciter. Exciter has AC. AC goes to this round thing you're seeing. That's what we call rotating diode. That diode converts it into DC. DC goes into the actual stator. And now this puppy spins. So that allows you to have brushless, magnetless, synchronous motor. But it's not self-starting. Everything else is awesome about that. It's just not self-starting. And I mean self-starting in terms of basically you just plug it into AC mains and it will not start. It will just, because again, if you have something that's supposed to spin at the same RPM as the frequency, it has to go from 0 RPM to that synchronous RPM instantaneously. Physics is like, nah, bro. So what happens? It tries to go, and then it's like pole changes, and it's like goes back. So that's why it's like, basically almost like if you have seen single phase AC motor, if the starter coil malfunctions, it's like same thing. So it's great, but does not like self-starting. And most systems, most motors don't self-start unless you are talking about some old brush designs. Most don't start. That's why you need encoders in almost all electric vehicle systems. You need encoders to tell the microcontroller, it's like, okay, this is where the rotor is. Please make a north pole here and slowly turn it so it can follow the system. Once it starts spinning, that's an easy thing. But again, electric vehicle has to go on, off, on, off, on, off. So they can use induction motor. They don't have to worry about that. Induction motor does not even need what you call encoder. Encoder for them would be for RPM calculation, not for feedback, where it's like, okay, this is how you spin it. So fundamentally, stator commutation does require calculations, and advancement in electronics allowed to have this sort of discussion. Before this, there was like induction, AC synchronous, the end. Now we had universal for everything else, and some other DC designs for locomotives, but nothing else. But only development of advanced electronics allowed locomotives to go from DC brush to universal motors to, no, they used to call it shunt motors. So those change from that shunt motors to induction motors or permanent magnet motors. And be mindful. One other thing you will notice that bearings go kaput. Bearings are like consumable in the system. One of the reason for that is shaft currents, because you are basically creating magnetic fields and changing so much with it, especially if you are driving with VFD, is that shaft starts to act like a capacitor. It starts to charge up. And problem with that, it's a static field. It can charge up to bonkers voltage, like 3 kilovolt, 4 kilovolt. It does not have the oomph. It will just like mildly shock you. But it has enough that it can destroy the enamel coating. And again, that's how most of the time you are like, hey, why the heck wiring is burning if nothing bad happened? Yeah, there is a good chance, not guaranteed, but there is a good chance that shaft developed enough current and shorted the system. So all the high-end systems, something like this, they always have a brush that is physically, electrically connected to the basically rotating part, rotor, and grounding at the same time. That removes all the electrical energy, and that allows your bearing to last, because if you do not do that, most of the time bearing will literally have a lightning bolt happening inside it, and it will do pitting. Basically, you have a ball, you have this that is charged, and this is that is uncharged. It will create lighting, boom it, create a pit. That pit will now grind, and your bearing goes bye-bye. By the way, that happens in space also for some reason. And yes, NASA has lost a lot of gyroscope for that. So grounding shaft matters. If you want to make sure your cheap motor lasts forever, ground the shaft. So this is the principal operations of it. Now we come to the hybrid. Now hybrid is, let that be very clear, sometimes you just are not happy with the principle, right? One principle is just not enough. For example, people love induction motor, but they hate paying for it because it's too goddamn inefficient. Like, it could be more efficient, and even if you can handle the inefficiency part, you can't handle the goddamn power factor. It's bad, it's brutal. And especially if you have something that is running constantly, yeah, that's bad for your bank balance. So somebody came up in, like, 1800s, late 1800s, like somewhere around that time frame. It's like AC synchronous motor. Basically, you have an electromagnet and you have slip rings here. It's like, what if this becomes self-starting? How would you self-start it? Be mindful, semiconductor does not exist. So they're like, hey, put an induction motor squirrel cage onto the rotor. So that gives you the starting torque. After that, you energize the coil and ta-da, it locks it. Now, like, wouldn't induction create an issue? No, induction requires line to be cutting each other. It can't catch because there is no slip. It is in synchronous. So that becomes just a dead weight, or like, bit of inertia. So that's how we got self-starting AC brushless synchronous motor. So there is no magnet, it's self-starting, it has power factor of 1. Now be mindful, I'm saying power factor of 1 means it does have some way of controlling the current, because again, it has to monitor it and control it, and it can be done with vacuum tubes and all that. It has been done, or some person can actually just do it manually. And this is the backbone of synchronous conductor, which people use in high voltage DC transmission lines. It's like, where the heck you will get grid inertia. That's how you get it. So let that be okay. Hybrid principles are not uncommon, it's normal. That's how all your industrial big motors are designed. Then we come to the most mixing of two weird things is permanent magnet assisted synchronous reluctance motor. This is Elon Musk's current love. The older love was induction motor. This is the current one. Like, why? Well, magnets are great at low RPM. They hate high RPM. Now again, RPM as in their design RPM. Why? If you increase the RPM, basically you have magnet, you are going YOLO. The magnetic field is constant. You cannot control its strength. It will create back EMF. Now you can try to cheat around it, like what we call field awakening. It's not that great. In synchronous, you have the option where you just reduce the current that is going inside. You can maintain high RPM. Here, you can't do that. So that creates an issue. It's like magnets are great at low RPM torque, but not that great at high RPM. So somebody is like, hey, what if we use reluctance? Reluctance are epic at high RPM because again, it's reluctantly following it. It's just like, bro, me good, we got this. And it does not fight back. So what the hell to do? It's like, hey, put it at an angle and basically at low RPM, you use magnet to do the main heavy lifting. At high RPM, reluctance aligns to it. So it's no longer cutting the field. So there is no back EMF. It's a very clever tactics, I have to say. But again, be mindful. It does mean your computer has to know which domain it has to manage. It's not just like, okay, rotation, this is where the field should be. It's like, okay, what the field angle should be. Because again, like how induction has to always follow behind, otherwise induction power will stop. Here is the same thing. It's like little bit of angle has to be maintained properly. That angle is the control vector, whether you go into full reluctance mode or full basically magnet mode. So it does become more complex. That's why I said like most of the things are only possible because semiconductor is cheap enough now. So this gives you the advantage of having low RPM torque and high RPM oomph of reluctance motor. So, and you can mix whatever you want. You want to fry your brain, try to figure out a universal motor. No magnet. It works on AC and DC and self-starting and super easy to change the rotation direction. But be mindful, electrically noisy as hell. Again, split rings are split personalities. They are naughty. And again, it does actually cause sparks. So really not recommended, but it is one of the most like, whoa, motor is like, whoa. So again, my personal favorite is AC synchronous motor, generally the brushless one. Be mindful, this type of variant is used in Nissan cars, electric vehicles, and they do not have squirrel cage because again, they are putting a rotor there, they are putting a encoder and computation, so might as well just start it electronically, not from the induction. So hybrid is normal. So this was my presentation on basically how do we deal with the future of the motor. And again, I just wanted to make that because I've seen way too much discussion without focusing on the grander landscape of things. So I hope you have learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free. And as always, thanks for watching.